And we are back. All right, today we're going to talk about formal charge. And what this is used for is to evaluate non-equivalent Lewis structures. So first, we need to know, first, the number of electrons, the number of valence electrons on an atom. Number 1. Then, what we do, we assign the number of electrons to a particular atom. Okay, so we do those two things, and we come up with formal charge, and I'll explain what that is in a second. So you want formal charges as close to 0 as possible, and if you are not able to get a formal charge of 0, you want the negative charges, negative formal charge on the most electronegative atoms. So those atoms like oxygen and halogens. Okay, so formal charge is the number of valence electrons on a free atom. So let's say if we're talking about oxygen, we know oxygen always, so we're talking about oxygen always has 6 valence electrons. And then it's the number of minus the number of valence electrons assigned to the atom in a molecule. Okay. And what we do, we assume lone pairs belong entirely to the atom in question. So a lone pair equals 2 electrons, whereas shared electrons, they're divided equally between 2 atoms, so a bonding pair is equivalent to 1 electron. So let's say we have an oxygen that's double bonded with 2 lone pairs. So that means the number of valence electrons assigned to the atom in oxygen here, there's 1, 2, 3, 4 lone pairs. There's 2 lone pairs, so 4 electrons total, and then there's 2 bonds, 1 electron in each bond, so that means there's 6 total. So that means 6 minus 6. Here, the formal charge of oxygen would be 0. Same as if it was, but let's say now it's single bonded with 3 lone pairs, so 6 electrons. So that means 6 electrons here, 1, 2, 3, 4, 5, 6. There's 1 in the single bond, so that means the formal charge of that oxygen would be 6 minus 7, so that means the formal charge of this oxygen would be -1. Okay. So what we do to get the formal charge, you take the sum of the lone pair electrons, you count each one, and then you just take 1/2 of the shared electrons. So the assigned valence electrons when writing it out mathematically is the number of lone pairs plus 1/2 the number of shared electrons. And then the valence electrons, to get the formal charge, is just the valence electrons minus that. So you subtract the number of assigned electrons from the number of valence electrons. So if we look at the following molecule, 4-POCl3. So we want to look at the formal charge of each atom. So if we look at the central phosphorus, we know phosphorus has 5 valence electrons. We look, there's no lone pairs, 4 bonds, so that means 4 electrons contained there, so that means it has a formal charge of +1. And we know always the formal charges should always add up to 0 on a molecule. It's like the ionic charges in that sense. The charges always have to balance. Alright, then we look at each of the chlorines. So we know each chlorine on its own has 7 valence electrons. Now we count, they each have the same structure, 3 lone pairs, so 1, 2, 3, 4, 5, 6. Electrons with 1 in a shared bond, so that means 7 electrons, so each chlorine has a formal charge of 0. And then finally for oxygen here, we know it has on its own 6 valence electrons, and here there's 3 lone pairs, so 1, 2, 3, 4, 5, 6 electrons, 1 in the bond, so 7 altogether, so that means it has a formal charge of -1, and you'll notice adding all these up has an overall formal charge of 0. And this structure is correct since it places a negative formal charge on a more electronegative atom like oxygen. Another example of this would be something like SO4 2-, and we can figure out its structure. If we thought for SO4 2-, all of these were single bonds between the sulfur and the oxygen, we would get a structure like this, with each oxygen having 3 lone pairs of electrons. So in this case, sulfur would have a formal charge of, it has 6 valence electrons, it only has 4 bonds, so 4 electrons, it would have a formal charge of +2. So we want formal charges as close to 0 as possible, and if you look at each oxygen, it has 1, 2, 3, 4, 5, 6, 7 electrons, so 6 minus 7, each one would have a formal charge of -1. So none of these would have formal charges of 0, so that is not favorable. So that's why we know sulfur can have an expanded octet. We are going to form some double bonds here. So a couple of these oxygens will have charges of -1, but if we form 2 double bonds, now with this double bond, now sulfur has 6 bonds around it, so 6 minus 6, it now has a formal charge of 0, and each oxygen with the double bond, now it has 1, 2, 3, 4, 5, 6 electrons, so each of those oxygens now has a formal charge of 0, and then the single bonded oxygen, same as before, now that just has a formal charge of -1, and you'll notice those 2 formal charges of -1 add up to the overall negative charge of -2. So that's more favorable. There's lower formal charges, and those -1 formal charges are on the electronegative oxygen atoms. So the sum of the overall formal charges always has to be 0. If it's for a molecule. So the sum of those formal charges in a molecule has to be 0, or for a polyatomic ion, it's equal to the overall charge, which in that case for SO4 was -2. And if those non-equivalent structures exist, those with formal charges closest to 0, that's why the second one, the SO4 2-, why that one was more favorable, and you want a negative formal charges on more electronegative atoms like oxygen or any of the halogens. So that's why something like CO2, this is the more favorable structure because the central carbon here has a formal charge of 0, and each oxygen here has a formal charge of 0, whereas if you wrote it this way, here, carbon would still have a formal charge of 0, but the oxygen on the left would have a formal charge of +1. This one would have a formal charge of -1, and that is less favorable. Alright, that's all for today. See you next time.